Hey guys, if you're here, that means you have completed the orientation module. This includes the syllabus assessment alongside with the academic integrity quiz. So now we can get into the meat of today, which is 6.1. You can follow along with the notes posted in module 1 as 6.1 notes. Not all of it's filled out, but you will be able to fill it out as you finish up this video. So two rays form an angle. The intersection of these rays is called the vertex of the angle. Now we're going to use theta and phi as variables for any sort of angle measurements. So instead of x and y, thetas and phi, just Greek letters. So an angle is broken up into two parts, ray 1 and ray 2. If my first ray, I call that the initial side, and then it opens up to the second ray called the terminal side. If I am opening up in a counterclockwise direction from here, the initial side to the terminal side, being counterclockwise, then this angle measurement theta will be positive. Now, if I have my angle where the initial side opens up to the terminal side, but this opens up in a clockwise direction, like so, then this angle phi will be negative. Now phi and theta could be negative and positive. I'm saying that depending on which way the angles open up will denote if it's positive or negative. So now you have two types of angle measurement units. Similar to how we have feet, inches, centimeters, and meters, we have a unit conversions and whatnot for angle measurements. The two that we care about are called degrees and radians. When we talk about degrees, this is the one you guys are more familiar with. We will have a small little circle, kind of like an exponent, as my superscript of the number, next to the number. Right? Now for degrees, a circle will have an angle measurement of 360 degrees. Half a circle will have 180 degrees. Here's what that looks like. If I draw my circle, and the vertex of the two angles, or two rays, for the two rays being at the center of the circle, the initial side will open up all the way to the terminal side, but the terminal side is back where the initial side started at. So this is an angle measurement of 360 degrees, or if you turn around, all the way in one complete revolution. Half a circle, if my initial side starts here, and then I rotate or opens up all the way to the other side. That's 180 degrees. It's kind of like a little reflection, if you will. Boom. Now, the angle measurement unit we care a lot about for this class is called radians. Most of you guys are not familiar with it unless you've taken a higher level course already. But the idea of radians, mathematicians decided to work with a circle whose radius was 1. And what they found out when they calculate the circumference, how long it takes to travel the entire circle, they found out that was equal to 2 pi distance. Well, they decided to call this angle measurement for the entire circle the same as how long the entire circle was. So if the length of the entire circle is 2 pi, then the angle measurement for a unit circle will also be 2 pi radians. That's the angle measurement as well. Now this will not be the same if my circle is not radius 1. So now we need to know how to convert from degrees to radians, radians to degrees. Well, degrees don't really have a pi attached, so to turn it into radians, I want to have a pi, so I multiply by pi over 180. Radians has a pi attached, I want to get rid of it when I go to degrees, so I'm going to multiply by 180 degrees, or 180 divided by pi, because I want to cancel out those pi's. So here are some examples. So the first example is 60 degrees. I multiply this by pi over 180. To multiply fractions, you multiply numerator with numerator, denominator with denominator. 60, the fraction for that is 60 over 1. So 60 times pi, and then 1 times 180. So I get 60 pi over 180. This simplifies to pi over 3 radians. If I do this for 30 degrees, I multiply that by pi over 180. I get 30 pi over 180, which is pi over 6. And then I've done these other ones for you and whatnot. For 45 degrees, you get pi over 4. For 90 degrees, you get pi halves. For 270 degrees, you get 3 pi halves, right? Now, I will normally use radians or rad to denote it is in radians. If I do not use rad, or if I do not draw a circle on it for degrees, assume we are talking about radians. So next is turning these following ones into degrees. 5 pi over 4, to get rid of the pi, I'm going to multiply it by 180 over pi. Pi's will cancel out, I get 225 degrees. I can do that for 7 pi over 3 as well, pi as well, negative 4 pi, and notice this last one says 5 radians. You don't really see the pi attached, but we're going to still follow the same principle. We're going to multiply that by 180 over pi. Now, pi can be treated as a number as well, 3.14, etc. So we can round that, and then we get a calculation rounded to 286.48 degrees for 5 radians. All right? Now, what are coterminal angles? Coterminal angles are two different angle measurement, but they somehow share the same initial side and the same terminal side. So for instance, if I draw my initial side right here, this is the initial, and then I've constructed my terminal side all the way over here, terminal. Let's call this guy 30 degrees. All right, theta is 30 in this case. Well, I can have a coterminal angle with that, where it has the same initial side and the same terminal side, but it has a different value and angle. I might have looped over it once or twice or 3 times. Now, how do we know what angle this is? Well, because I looped around in a circle more than once, or at least once, this is going to be 360 degrees plus 30 degrees. So we find out that 30 degrees and 390 degrees are coterminal angle because 30 degrees plus 360 degrees give me 390 degrees. They will land at the same spot. Now likewise, I can also rotate in the clockwise direction, which means negative, or I can subtract 30 from 360 and I get negative 330 degrees as my other coterminal angles. You have infinite amount of coterminal angles. They're just multiples of 300 or negative 360 degrees. I can also do that with radians, not just degrees. So instead, if I had drawn my initial side right here, and then boom, terminal. Let's make this angle though, pi over 3. To find that coterminal angle that's next to it and whatnot, well, I'm going to loop around once. Boom. I have to add that by 360 degrees, or in radians, add that by 2 pi. So, over here, I've already done the calculations. If I did 2 pi plus pi over 3, you have to know how to add these fractions. You got to turn 2 pi into a fraction, and then get least common denominator. So, 6 pi over 3 plus pi over 3, which is going to be 7 pi over 3. The denominators do not need to be added up at all. It's just the numerators. Alright, so you can do that as well with radians. Moving on. We got length of arc, or arc length for short. I guess they're the same, I don't know. But we have the formula S equals R theta. This S represents arc length. And then R stands for radius. And theta represents angle in radians. It must be in radians that you're working with. If it's in degrees, you can't use this formula. You have to turn it into radians. So here's what arc length looks like. What if instead I had this right here? Let's say I have the center being the vertex of the two angles. Boom, bada bing. And I wanted to calculate the distance from here to here, x, where the angle opening is formed. I wanted to calculate how long it takes to travel that guy. Well, I need the radius, and the radius is just any of these rays in particular to the edge of the circle, and I need to calculate this theta. If I have those two things, I just multiply them, and then I get the arc length, which is very nice. So let's do an easy example on that in particular. Boom, 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 boom. Let's do... Oops. What if I give you something like this? This is 5 centimeters, and this is 20 degrees. And I wanted to calculate this arc length right here. Well, in this case right here, we're going to use the formula, but the only problem is 20 degrees is in degrees and not in radians. So we need to turn 20 degrees into radians. And if we do so, we get pi over 9. Now using our formula, this means the arc length S, which I call x in this case, is 5 times pi over 9, which is 5 pi over, it shouldn't be 4, it should be 5 pi over 9. I don't know why I messed that up. Oh well. Boom. Alright, so let's do another example of this in particular. What if instead I had, let me erase this now. I had something like this. I have an angle measurement right here, and this angle measurement is 2 pi over 3, but the arc length, how long the opening is, in particular, is 90 feet. And I want you to solve for r. So we're going to have to kind of work backwards in a sense. And to work backwards, and just so you guys are aware, 90 feet is the distance from here to here. It's distance, not angle. Alright? So in this case right here, we have to solve backwards and whatnot. Now, thankfully, the angle I've given you is already in radians, so we do not need to do the conversion. But when we do the calculation and all that stuff, we get 90 is equal to r times 2 pi over third. And then to solve for r, I have to divide both sides by 2 pi over thirds, which means I multiply by the reciprocal, 3 over 2 pi. And if I do that, I get the radius is equal to 135 divided by pi. Feet. Because that was the last unit we were in. Alright, so that gives you an idea how to do the other type of calculation. Now, that's arc length. We're going to go into sector area. Sector area, the formula is A is equal to 1/2 r squared theta. So, what is sector area? It is a piece, an area of a piece of the circle. So, I have r, I have theta right here, and the sector area looks like this portion. The shaded in region for the angle. Alright, so let's do an example of that. What if instead I give you this? And I said the distance from here to here was 4 centimeters. So I've given you a diameter, and I've told you that the diameter is 4 centimeters, and now I want you to find the sector area of the top half of the circle right here. How do I figure out that area? Well, first we need the radius. The radius is half of the diameter, so half of that is 2. And the angle measurement I'm working with, since we're working with half a circle, this is 180 degrees, but I have to turn it into radians, which is pi. So in my formula, I have 1/2 times 2 centimeters squared times pi, which is going to be calculated as 2 pi centimeters squared. So that's the area in that case for this sector area. Alright, and we're almost done. So now we're working with trigonometric ratios. These are regarding these functions, sine, cosine, tangent. Where are they at? Right here. I don't know why they did that. Alright. And I use this little, I guess, notation, SOHCAHTOA, etc. to kind of help you understand this and whatnot. So, before we move on, what we need to understand with these trigonometric functions, a function is something that has an input and an output. Now, there's more details to it, but that's the main idea. I have an input, and I do something to that input, and it'll spit out something. In particular, the input, we call these guys the angles. My function, sine function, cosine function, tangent function. So let me write that down. This is the sine function. This is the cosine. And this is the tangent function. Now they're going to be abbreviated, of course. That way it's easier to write. But what I throw inside these functions are angles. Now what they spit out are these little words right here, which represents side ratios. These trigonometric functions are for right triangles. So here's an example. I have a right triangle in particular. Boom. Right triangle has 90 degrees in particular for one of the angle measurements. Now, each of these sides will have a name. The longest side has the name hypotenuse. The other two sides, or the legs of the other two triangle, or of the triangle, can either be the opposite side or the adjacent, depending on what angle you threw into your function. So if I throw in my function, if I throw in theta right here, if I ask you what is sine, and I need an input, it'll spit an output. If I ask you what is sine of theta, I want the opposite side length divided by the hypotenuse side length. If I want to do cosine of that angle measurement, I'm going to do the adjacent side length divided by the hypotenuse side length. A over H. If I want to do tangent of that angle measurement, I'm going to do opposite side measurement divided by the adjacent. I almost messed that up. Adjacent side measurement. All right, and it does matter what angle you're talking about. So let's do an example of this, putting this into practice really. So I'm going to draw a triangle in particular, and I've already filled this out and whatnot, so get a little first glance. Why does it always do this? Let's draw a triangle. A right triangle, has to be right. I'm going to draw theta here. Now, when I say opposite, we're going to look at the angle we care about. In this case, it's theta. We're going to care about it, and then we're going to go directly across it. This is called your opposite side from the angle theta. The adjacent side is the side that touches with the angle that is not the hypotenuse. This guy is the hypotenuse because it's the longest side, so the one next to that is the adjacent. Now, what happens if I use a different angle measurement? What if I said the angle in my right triangle was over here? Boom. If it's over here, the opposite side will change, likewise the adjacent side. The hypotenuse will always be the longest side no matter what. However, opposite of this angle right here will be located down here instead. Likewise, adjacent will be up here. So it does matter where the angle in the triangle you are referring to. So we'll do an example of some calculations. Let's say I give you a right triangle. Let's say this guy right here was theta. I care about this angle theta right here. And then let's say I'm working with, I don't know, 21. And then the other one is 28. And I want you to calculate sine of theta, cosine of theta, tangent of theta, all of these ones listed. Let's say phi was here too. Let's just put phi here. That way we know. A triangle. Then how do I actually calculate sine of theta? Well, it's opposite over hypotenuse. I'm going to look at theta because that's the angle I care about for this question. The question says sine theta, not sine of phi. So I'm going to look at this guy. I'm going to look directly across it. That guy is 21. That's my opposite. So opposite is 21. Remember, this guy is opposite over hypotenuse. And then the hypotenuse is 35. But how do I know it's supposed to be 35? I didn't give it to you in this problem. Well, you have to calculate that out. By Pythagorean theorem, we know that 28 squared plus 21 squared gives us 35 squared. A squared plus B squared equals C squared. All right. So if you did this calculation, A squared plus B squared equals C squared, you get that the hypotenuse will be 35. And that's how we get that measurement. Now, we can calculate these other side ratios. Now, the first three uses the input theta. So I'm going to use the same opposite and adjacent, etc. I just need to know which one I'm working with. Cosine is adjacent over hypotenuse. So the adjacent side is 28. Let me fix this up. 28 over 35. And then tangent is opposite over adjacent. Opposite was 21. Adjacent was 28. Now let's do it with the phi symbol, the phi angle, the angle up here. The hypotenuse should still stay the exact same, but now the adjacent and opposite might be different. Opposite of this phi is 28. So this is 28 over 35. And then adjacent of this phi is 21 over 35. And tangent of this phi is going to be 28 over 21. So we get that idea. So these are the three main trig functions. Now, with these trig functions, mathematicians decided to reciprocate them. What does reciprocate means? That means they decided to flip their ratios. So instead of opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, they reversed it all or flipped it upside down. You have hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. So let's work with the secant function. SEC. The secant function is the reciprocal of your cosine function. It is flipped. Instead of adjacent over hypotenuse, it is hypotenuse over adjacent. But be careful. This is working with theta. So we have to look at theta. What is the hypotenuse? Well, that's 35. And then what is the adjacent of this angle theta? Well, that's 28. And then I can do cosecant, which is the reciprocal of my sine function. And this is opposite over hypotenuse, so I'm going to flip that. That's hypotenuse over opposite. So now this becomes 35 over 21. And then cotangent reciprocal is tangent. So this is going to be 28 over 21. Okay? So that's the main idea with calculating these trig functions and all that stuff. You're going to take an input, which is your angle measurement of the right triangle, and then it's going to spit out a side ratio. Now, how do we apply this in applications and whatnot? Well, let's solve some problems using right triangles and trig. So let's take this example. I draw a right triangle here, and then I say this angle right here is 50 degrees, and then I give the hypotenuse to be x, and then the one on the base is going to be 18. Right? That's the length of it. And then how do I calculate x? How do I figure out how long the hypotenuse is? I can't do a squared plus b squared equals c squared because I'm still missing the other side. So I have to use something with trigonometric ratios. So the first thing you got to do is identify what type of sides you are working with or do you have of interest. This is the hypotenuse. And now this 18 in relation to this 50 degrees is the adjacent. In relation to the 50 degrees. So I need to use a function that has adjacent and hypotenuse. I'm going to use the main three functions, sine, cosine, and tangent, so we're going to choose between one of these three. I don't want to use the reciprocals for this. It might be too complicated. So if we use this, we get cosine function. The cosine function uses adjacent and hypotenuse. So I'm going to write cosine of something. It has an input, and it's going to spit out a side ratio. So I need to fill in what's the input. Well, the input is the angle measurement, 50 degrees. Now, what does it spit out? It spits out adjacent over hypotenuse, which is 18 over x. Boom. Now I can solve for the hypotenuse x. Now, this cosine of 50, they stay together. They are one object. Do not split up the 50 degrees with the cosine. Do not do 50 plus 18. Don't do any of that. They stick together. They're one object. So when I do the calculation, I'm going to multiply both sides by x. And if I multiply both sides by x, etc., then I can divide both sides by cosine of 50 degrees, and I get x is equal to 18 divided by cosine of 50 degrees. Now, when you put this in your calculator to do the math and whatnot, make sure you're in the right mode. Calculators default to radian angle measurements. 50 degrees is a degree. So you have to click on mode, and you have to scroll down to where it says degrees. And then you can do the calculation. So the hypotenuse is roughly 28 measurements long. Alright, let's take two more examples and then we'll move on. So the next two examples I want to work with is this right triangle where this side is 6, the bottom is x, and then we have the angle that we're commonly used to, 35. I don't know, I'll draw this way. I don't really care which way. Well, I guess if I'm accurate, I should draw this way. Doesn't really matter to me right now. And they're both right triangles. They have to be right triangles. This guy is y, this guy is 7, this guy is 20 degrees. 20 degrees is up on that triangle this time, so not on the bottom. Alright, so let's look at the first one, right here. We have to figure out what's of interest. Well, in relation to this 35, this 6 right here is opposite, and then this x is the adjacent. So we're going to be using something that uses opposite and adjacent, which is the tangent function. So I need to already start by writing tangent of something parentheses equals a side ratio. Now I got to figure out, what do I throw inside this tangent function? Well, the input is 35 because that's my angle measurement. So I throw inside a 35 degrees, and it spits out the ratio opposite over adjacent, which is 6 over x. I need to solve for this x. So I'm going to multiply both sides by x. Multiply both sides by x. X is equal to 6 over tangent of 35 degrees if I divide out tangent of 35 afterwards. Alright, remember they're one object, they stay together. And then if you did the calculation, this is roughly 9 feet, 9 centimeters. I don't know what units we're working with. Alright, now we're working on this guy right here. Well, the relationship between 20 and y in this case, this time, this bottom one is opposite. This guy is the adjacent because the hypotenuse is along the side. So now I'm still using the tangent function because I have opposite and adjacent. So tangent of something equals something. Remember, my input is the angle measurement. So I'm throwing in 20 degrees here. Now I spit out the ratios. The ratio in this case is y over 7. And I'm solving for y. So all I need to do now is multiply with 7 to both sides. And then I get exactly what y is. So y is approximately 7 times tangent of 20. Now you should put this in your calculator. Do not do 7 times 20. You cannot do that. This is around 3 feet. So hopefully those examples help out and whatnot. So the next time we're going to talk about the special right triangles, the angle of elevation, and angle of depression. But for now, let's leave this as a stopping point, and I will catch you guys in 6.2. Take care. Bye.